And they're based on a collaboration with Denis Comelli and Marco Celoria, and early on with also Guillermo Ballesteros, that was basically here as a postdoc. I also like to emphasize that Marco Celoria is a PhD student at Becky Lapia at the Grand Sasso Science Institute, and is going to be looking for a postdoc soon. So keep in mind that. Okay, so I guess, I mean, it's probably we don't need many motivation for that, because otherwise we are not gonna having this kind of workshop. So clearly the question, what if the dark energy is not a cosmological constant? Okay, of course there will be a number of probes that are going to test the nature of dark energy. Maybe will be successful to say something more than just constraining the equation state. We'll see. And clearly, on the theoretical level, there are really a huge number of proposals. We just have a limited number of that. That in the first talk today, we have a huge kind of cartoon-like picture of all the possible modification of gravity that was considered before and dark energy model. So also, I think we have to keep in mind that the limited number of observables that will be available are limited, so that typically, naturally, there will be a huge degeneracy between at least some of these theories. Okay, so I think it would be useful to have a very simple theory that is general enough to have let's say a rich phenomenology, and that is based on an effective description, and in which symmetries play an important role. Okay, so this would be the goal. Well, a starting point, typically of effective field theories, is basically what are the symmetry of your theory, and what kind of fields you use to realize them, right? And so the basic assumption that I'm going to use is that the equation of motion can be derived from an action principle, and I have diff invariance. Okay, that will be the basic stuff. And we know that in 4 dimensions, if the metric is the only field, well, there is nothing really. There is really very little space left, and you end up with the GR, and you have 2 degrees of freedom that are propagating. Okay, adding a cosmological constant does not really change the number of degrees of freedom. Okay. Okay. Now, of course, if you add fields, you get more degrees of freedom. That's also very simple statement. Okay. And what I'm going to do is just take the simplest option. I just add a number of scalar fields. And again, to be as simple as possible, I'm going to take them to be minimally coupled with gravity. Okay? And I will also impose that these scalar fields have some internal asymmetries. Okay? And in particular, I'm going to use the fact that these scalar fields have shift symmetry. Okay? So they shift with a constant value, okay? And I'm going to take the number of this scalar field to be 4, just because in this case the conservation of the edge momentum tensor that coming from this scalar field theory is equivalent, completely equivalent to the equation of motion. So if you combine shift symmetry, the fact that you have 4 scalar field, essentially all the dynamical information about the scalar field is contained on the energy momentum tensor. Okay, I'm gonna also I will impose that the Lagrangian that describes the scalar field would be rotational invariant. Is an internal rotational invariant, so I just basically transform this field as they were coordinates, and so these are just the SO3 rotation, and I will impose that the action, the Lagrangian, if you like, is invariant. Okay, so it turns out that these hypotheses are enough to derive a quite rich structure. In particular, has been known for a while. Such a theory describes the effective dynamics of media, like fluids, superfluids, elastic solids, and supersolids. Okay, and you can consider a derivative expansion. So what I'm going to speak about, I will just take in the first non-trivial term, so I will just consider a single derivative acting on each field. Here are just a number of early references that come from the 80s and that's been revitalized recently by, well, essentially these people here. Okay. Let me just give some kind of classification of operators. So essentially, this is the basic object you can consider the first order. So you just essentially you contract the derivatives of the scalar fields. So sorry for the I'll keep changing notation between capital phi and var phi. So this is the basic object you can construct. Okay. So these are scalars. Okay. A, B goes from the capital Latin letter go from 0 up to 3. Okay. And you can have a bunch of operators. You can see you have kind of the spatial matrix built with the derivative of the spatial field. Then you have a kind of vector-like components. You can have scalars, and then you have the determinant of this matrix, and so forth, so on and so forth. So another important object that you can construct is a velocity field. Okay, it's a four velocity that is basically describe the velocity of the fluids, and this is the scalar fields are basically are constant along the flow lines of this vector field, and that's basically tells you you can interpret the phi a, the spatial part of the scalar fields as they were coordinates of this medium that is embedded in space-time. Okay. Then you can also have this combination of derivatives of the temporal scalar field that essentially will play the role of a superfluid component. Okay, and out of this object, the phi z, you can get another velocity vector that physically will represent basically the superfluid, if it's present, superfluid velocity field. Okay. So essentially, the most general Adelaide order Lagrangian that respect the shift symmetry and the internal rotational invariance will be a function of these scalars. Okay, so this is B is missing, but there should be a B here. So B, X, Y, the taus, and the Yn. These are just combination. Okay, and okay, as a kind of picture. So as I said. You can imagine, sorry for the change of notation. So this scalar field can be interpreted as the coordinates of the particle of the fluid media, whatever it is, that is embedded in space-time. And the temporal scalar field, the phi 0, is just the medium clock. And clearly, depending on what kind of configuration you choose for your scalar field, there will be a spontaneous breaking of Lorentz invariance. Clearly, when the fluid is there, you are breaking, by definition, you're breaking Lorentz. Okay. On the other hand, if for some reason the fields fluctuate around 0, you just have a standard scalar field theory, nothing more, nothing less. And what is interesting is that, well, it's been known again for a while that the fluctuation of this guy here are just the Goston boson of broken translation, and these are just the phonons, the elemental excitation of the fluid. Of course, so this theory has no attempt to give an underlying interpretation of what are these degrees of freedom, just a purely effective description. We are kind of looking at the very large scale, the scale that are relevant for dark energy. We might see we kind of think that this can be interpreted as a medium. This picture has been successful for because we do the same for photons, for dark matter, for basically whatever things has been put on the energy momentum tensor. So we are trying to do the same for dark energy. So it's a very in a sense simple and minimal, I'd say, hypothesis. Okay? Yeah, sure.
May I just interrupt you?
Yeah, sure.
And make a comment?
Sure.
I think it's a bit confusing to say that they're Gostons, because the Goston theorem implicitly or explicitly states that it depends on time translation invariance. It's not really applicable applicable for time symmetries. It's one thing.
Yeah, it is. There is a Ghost version also for space-time symmetries. Actually, the translation, the broken translation are just, the phonons.
Your fluid could have a stationary flow, and those spies are not observable because if it is a fluid, you don't couple to them directly. Then the fluid would have explicit time translational invariant in the stationary flow. It would be killing vector there, and still there would be phonons.
You're talking about what the temporal the temporal field, or also the spatial bonds?
Take them in one field, right? So to make it superfluid, it could have stationary flow. It means that everything what is observable is actually stationary. So there is a killing vector, there is time translational invariance, and clearly there are phonons. I think it's a bit exaggerated, right? Because what you're saying is that there is a breaking in the fields in which you actually only parameterize things, in the fields which are not measurable.
Well, actually, that's an interesting point. We'll see later that actually it's possible. I mean, it's interesting what you're saying. That actually, I mean, we'll see that actually it's possible. Actually, it's the best way to do it. Instead of formulating the equation of motion in terms of those pies, this kind of Goldstone fluctuation, and because the equations are very messy, it's possible and actually very useful to use it observable. And we're going to see in a few slides that actually that's precisely what we do. Use thermodynamics. So you use, let's say, the gravitational potentials, okay, and the particle number and the entropy per particle density. Okay. So in what follow, I will always I only use observables, at least what we think they are observable. So physical observables. So yeah. So probably maybe this gonna answer your question. Okay. So in practice, I won't use much this kind of picture in which the pies are the Goldstone boson or broken translation. Okay. So then we can discuss whether theoretically those are or are not the Goldstone boson or broken translation. Okay, so let me just give an example. Okay, the simplest example you can imagine, perfect fluids. So you just you can see that by imposing a suitable symmetry, basically it's a spatial volume preserving internal diffeomorphism. So it's really a big symmetry in the internal symmetry. You end up having only two possible operators, this B and Y. Just a reminder, B is just this guy here. Just the basically is the scalar is made of the first derivative of this phi A, the spatial fields, and this is just the derivative of the of phi 0 along the fluid velocity. And you can easily work out what is the energy momentum tensor, and of course it's the energy momentum tensor of a perfect fluid, in which you can read out the density and the pressure. And notice that it's not about entropic fluid, so in general there will be entropic modes. Of course, the entropy per particle in this case is conserved because it's a perfect fluid. Okay? And what was also interesting that this formalism allows also to derive the thermodynamics of this object. So I don't have the time to explain it, but you can interpret it Y as the fluid temperature, B as the particle number density, and the derivative of Y with respect to Y as the entropy per particle. So basically there is a mapping between the effective field theory operators that you make from your scalar field theory into basic thermodynamic variables, and you can check that all the thermodynamics law are satisfied. Okay. Okay. Here just a kind of complicated table to indicate what kind of symmetries, internal symmetry you have that restrict the various type of medium. So if you have, let's start from perfect fluid. So you have volume preserving diffeomorphism, talking about internal symmetry. So you are changing the spatial scalar fields in a way that the volume is preserved, and you also ask this kind of shift, time special field dependent shift in the temporal scalar field. And if you impose that, you get that basically only B and Y are allowed, and those are perfect fluids. Okay, so if you modify slightly the symmetry, you can also turn on other operators, and those operators correspond of a superfluid. And you can see it from either the edge momentum tensor, but also from the degrees of freedom that they're propagated, as we see in a couple of slides. And then if you basically do nothing, so there is no symmetry that are imposed except shift symmetry and internal rotation, you have all the operators are allowed. You have what they're called solids. They are supersolids. They are solid depending on whether this Y enters or not, whether also the X operator. So basically the idea is X is somehow associated with the superfluid component. Then if interact with also the solid degrees of freedom, it becomes a supersolid. I mean, you can. I mean, there's nothing really fundamental, just the names, if you like. Names that correspond to the energy momentum tensor of those objects. Okay. So there are so the energy momentum tensor generically can be written in this way, and depending on the essentially it depends on the derivative of the Lagrangian with respect to the basic operators. Then you have a different type of media. Okay. So essentially, superfluid have this is sometimes called the heat flow. There is no heat flow. There is no anisotropic stress. And on the other hand, for solid, you do have an anisotropic stress, but the heat flow is different from zero. And for superfluid, you do have an anisotropic stress, but the heat flow is zero. And and for supersolid, everything is different from zero. And again, this is achieved either you can see in two ways: by symmetries, just looking at what kind of operator are permitted by the internal symmetry, or in practice by just looking at this parameter that are derived by taking the derivative of the Lagrangian with respect to the basic operator. So there are basically four these are at the dimension of the mass to the mass square. I just write down just for yeah. Just the anisotropic stress. I divide by a kind of perfect fluid part, which is just h mu, the projector, and then what is left. Okay. Just for yeah, exactly. All right. So those just a bunch of parameters. So once you give the Lagrangian, you get everything. So let me go to the scalar perturbation, because we're most interested to cosmology. I'm just looking at the perturbation around FRW, okay, and in the background level, the Stuckelberg, what you want to call the temporal scalar field, depends only on time, and the spatial Stuckelberg, or spatial Goldstone, if you like, are just xi, and you can easily see that because only the derivatives appears in the energy momentum tensor. So clearly, this gives you an energy momentum tensor of a perfect fluid that is consistent with the anisotropic and homogeneous energy momentum tensor. Okay. For the metric, I just using for simplicity the Newton gauge, but you can do everything even in a gauge invariant way. Okay. And there are two basic equations. So in principle, you could expect that there is a very complicated equation of motion involving the pi's, but actually, if you look carefully at the equation of motion, you can rewrite them by using essentially the hint of thermodynamics. So it turns out that everything can be written down in terms of basically two fields, the standard two fields, that are the gravitational perturbation plus, okay, plus there is another ingredient, the entropy per particle, delta sigma, is the perturbation. Of course, there are also the velocity fields, but I'm just looking at the scalar perturbation. You can also work out the tensor and vector perturbation. So this is the standard. So you have, first of all, in general, for a generic fluid, generic media, you have, because of the anisotropic stress, this is the M2 that controls the anisotropic stress, the two Bardeen potential are different. This is kind of standard. And they are related, and the difference of the two Bardeens are given by this relation. And again, in which this A0, A1, and B, they are function of the momentum and the background quantity. Okay. W is just the equation of state. yeah, this is a fluid. So you have
I mean, can it be
P and rho. It's just the P divided by rho.
whole? I mean, can it
The
be
whole.
-1? Can it cross -1?
Okay, then we discuss. Okay, okay, I will comment that later. Yeah, it's a good point. So this is the standard equation of motion for the Bardeen. So in the case of fluids, okay, these functions are 0 and 2 is 0. So you have simply the only difference with respect to the standard picture. You have this entropic contribution. So essentially, there's a source that coming from the fact that the fluid is not barotropic in general. So there will be entropic perturbation. The force can change the expansion history. Okay, and in case of a perfect fluid, delta sigma is just a constant. Okay, so this is just a constant. On the other hand, if you have at least a superfluid, this entropy per particle becomes dynamic and satisfy this kind of this a second order equation. And so essentially, this is a closed system. You have just to provide the background quantities. And this is just the standard sound speed that is computed in the standard way. And there is another kind of sound speed. This is the ratio of these two mass parameters that controls basically the entropic contribution. If these two sound speeds are the same, then you don't have any entropic contribution. So, the dynamic content can be studied quite easily, though in the general case the equation can be rather complicated, but not terribly complicated. Okay. Okay. What about the question of W plus 1? Okay. This is there is a kind of general statement that it's very general. That basically when you cross or you pass the W plus 1 0 or less than 0. Unfortunately, we know there's a very nice paper by Nicolis, Ratazzi, Tubowski, missing probably some Gregoire, and saying that basically you typically end up having instability. You can check easily if you go in the decoupling limit, so you just consider simply the Stuckelberg field, okay? You can see immediately that when you hit rho plus p equals 0, typically there are instabilities, okay? So theoretically, you can work out what kind of equation. This, of course, those equations are being worked out in the case in which W plus 1 is not 0. You can do, okay? But typically, you do have instabilities, okay? So, but yeah, you can easily construct objects that have W plus 1 equals 0 exactly at all orders, but perturbation depending on typically they have some problem. Not always, but okay. We have been looking to this kind of things. Yeah.
If you have this kind of fake fluid with W equals
Yeah.
minus 1,
Yeah.
is it still a dynamical system?
Yeah, it is. We should hopefully publish a paper soon. But yeah, it's possible to have of course, it's not a perfect fluid. Yeah? That's for sure.
And what's the sound speed?
Sound depends. Can be. The sound speed 0. Typically, it's 0. Yeah, because W is constant. It's 0.
So but basically then it's equivalent to dust. With,
No, because the vector perturbation are different. So it's not dust. Yeah, it's really weird. They are strange. Okay. Yeah. Well, depends. Essentially, typically the Hamiltonian is not bounded from below, so you could call it ghost, gradient, whatever. But yeah, that's.
No, I think here generically the sound speed would go to imagine.
Yeah, if you like. Yeah, if you like. It really depends. Well, we were discussing with Sergei last night. It depends really on the gauge. Okay, if you the unitary gauge well.
No, your sound speed becomes imaginary, so it shouldn't depend on the gauge because that's your physical.
No, what I'm saying that, for instance, if you take the coupling limit, you just consider only the Stuckelberg. Actually, you don't see a ghost. You see a gradient instability. Okay, so even when rho plus p is equal to 0, as soon as this m1 is positive, there is no problem. m1 and 0 are positive, but on the other hand, there is a gradient instability. So the mass of this fluctuation tend to be negative. So then you can call it. But on the other hand, if you perform the computation slightly different way, you start from, let's say, you turn on the gravity, and then you basically do that what has been done by Rubakov, and then you realize there is a ghost, so you can yeah, it's kind of weird, but that's what happens. But clearly, what is the physical sentence that the Hamiltonian is not bounded from below. Okay, that's at the end of the day what happens. So results: the internal rotation. When you have just internal rotation as an internal symmetry, you have a supersolid, and there are two dependent scalar perturbation, namely essentially one of the Bardeen potential and the entropy per particle perturbation. And the perturbation are typically non-adiabatic. And notice that even you start from adiabatic perturbation because delta sigma satisfies second order equation of motion. You can develop autonomously a non-adiabatic perturbation. On the other hand, if you impose volume preserving diffeomorphism on the top of internal translation, you get fluids, and fluids in general can be in the case of perfect fluid you have just a single degrees of freedom. Okay, in the case of superfluid you have also the entropy per particle again. They play in the role. Then if you combine essentially solids with a superfluid component, you get what we call a superfluid, in which basically everything is on. So you do have anisotropic stress, you do have the entropy per particle that is propagating is feeding back the equation of motion for the gravitational potential. Okay, this is just depending on the value of the mass parameters, just what happened. You can also classify in terms of thermodynamics, thermodynamical fixture instead of dynamical one, but the story is the same. Okay. Conclusion is that I'd say that this kind of picture makes a quite general framework in which you have enough freedom to explore essentially a lot of type of modification. Okay, yeah, I'm gonna finish before, and they're very simple. So clearly, the fact that everything is minimally coupled makes things rather easy. So there will be no modification to the Poisson law. That will be standard. Okay, but there could be anisotropic stress in the case of you have solids or supersolids. And so generically, there will be 2 degrees of freedom in the scalar sector. Okay, and there's another thing that I don't have the time to discuss in detail, but I mean, this kind of theory is just a massive gravity in disguise. Of course, Lorentz breaking massive gravity. So you can go to the unitary gauge, you can use the Stuckelberg fields as a coordinates, and basically you end up with this mass parameter I was mentioned are just mass parameters for the various component of the metric tensor. Okay, so M2 is the mass of the graviton. So actually, if you look at this tensor perturbation, M2 just modified the dispersion relation of the graviton itself. Okay? So the feature of one of the main features of this picture is that, for instance, gives you in a very consistent way the entropic perturbation. They are completely, its dynamics is completely fixed by the equation of motion. You don't have to to make assumptions. Everything comes really from principle. Also, it's interesting that, in a sense, the 6th mode of mass gravity in this way is as a thermodynamic interpretation. It's just in this picture is basically the entropy particle perturbation of this very strange fluid. Okay, and clearly the next step would be try to understand what kind of constraint you get from the future surveys. Thank you.
I remember when Nicolis was doing this, they had this problem that the vorticity had 0 sound speed.
Yeah, sure. But so classical is not a problem. I mean, it's only for perfect fluids, because perfect fluids, it's just classical stuff. Vortices do not propagate because you have in volume preserving diffs. There are such a huge symmetry that actually makes the vortex kind of frozen. They just can move at the classical at the.
Okay, but if you add these extra the new operators that.
So here they say vectors are okay. So they propagate with certain. Of course, if you consider the M1 that goes to 0, you are back to the fluid picture. On there, of course, you have the vortex are. It's just a perfect fluid, so vortex cannot really propagate. That's just a classical picture. I mean.
Just a quick question, because it's interesting for the phenomenology, technical issue. So if up to instabilities, if W is less than -1, the temperature and the entropy can be defined. I mean, they are negative, positive.
Depends really on the background. Typically, it depends also on the fluid. But yeah, they can be defined. It's kind of weird because, okay, technically speaking, from a thermodynamical point of view, okay, that when rho plus p is negative, okay, thermodynamics is, stops to work. So clearly you are wandering in a territory in which, you don't know what's happening. But you could go, for instance, typically the CB, this kind of sound speed related to the entropic perturbation is negative, typically. So yeah, but technically speaking, even if you look at thermodynamic stability, there is no thermodynamic stability there. Okay, so sorry.
Yeah, just a basic question.
Yeah.
I just want to know what kind of model can you, reproduce, or which kind of theory, can you not reproduce with this approach? So
it depends on what you want to look at. I mean, if you want just to look at cosmology, well, you just need to know these 4 parameters, and if you know those 4 parameters, typically will be time dependent. Okay, you know everything. You know the sound speed. You know so you can solve all these equations. If you look from a, let's say, more fundamental question like, can I produce the Lagrangian for, let's say, a real fluid? The answer is yes, and it's, as Alex was mentioning, it's kind of complicated because those kind of beasts tend to have very complicated Lagrangian. So it depends really what is your perspective. Just cosmology, then you can forget about at least a linear perturbation theory. You can forget about the whole exact Lagrangian and look at just the quadratic expansion, and only those parameters matter. If you want to ask yourself, can I model a superfluid in a realistic way? Yeah, the answer is yes.